Hello friends, I am Amir Nizami and I thought of making a series of lectures on Euler-Bernoulli beam. So in this lecture 0, we will start for just introducing the syllabus, what we will complete for this Euler-Bernoulli beam. So let's start. So in lecture 1, we will use the Euler-Bernoulli assumption, Euler-Bernoulli assumptions to get the displacement fields. Okay, so how the assumptions helps us to get the accurate displacement fields for the Euler-Bernoulli beam. Okay, displacement fields. So this would be our lecture 1. Then lecture 2, we will see the derivation of the governing equations. Derivation of the governing equations of beam, that is Euler-Bernoulli beam. What is that governing equation? We remember EI d for Wx by dx to the power 4 equals to q of x. Okay, minus q of x equals to 0. So we will just derive it using what? The first is lecture 2a, that will consist of lecture 2a direct method. Okay, that is the direct method. Lecture 2b will be consisting of principle of total potential energy approach, principle of total potential energy or total potential energy approach, potential energy approach. And then lecture 2c will be consisting of principle of virtual work, principle of virtual work. We generally say the first one as total potential energy approach. Okay, so in these 3 lectures, lectures 2a, 2b and 2c, we will just derive by 3 different methods the governing equation of the beam. Okay, in lecture 3 we will discuss the solutions of Euler-Bernoulli beam. Okay, so solutions जो है some numerical problems we will solve. So in the lecture 3a we can say, okay, so we will have the solution for the exact solution. We will find the exact solution using the boundary conditions or integration method, direct integration, and we will find the unknowns and apply the boundary conditions there. And then the next is what we have, lecture 3b, which have the derivation of load type. Okay, just like UDL, uniformly distributed load, sinusoidal distributed load, point load. Okay, using the Navier's techniques. Okay, so basically we remember that what we have QM, we have different values for UDL, for sinusoidal distributed load. Okay, just like Q0 is for the SDL, and some different values for the UDL, and similarly something different for the point load. Okay, so we will derive it how we approach this QM so that the deflection WM can be known to us. Okay, so it needs the Q of M value. So Q of M depends upon the type of loading we have. So either we have UDL, sinusoidal distributed load, or point load, that depends upon those. So we will do this. Okay. Then the lecture 4. So now we will use the finite element method. We'll introduce finite element method. Okay, for this Euler-Bernoulli beam. Okay, so we will start with the lecture 4A, which consists of the discretization of element, and then finding of the Hermite shape functions. So the shape functions what we use, the Hermite shape functions. So how do we get it? Hermite shape functions, we will see. So Hermite shape functions. Okay, and it's plotting. How we plot the Hermite shape functions. Okay, so basically how we discretize it and how we plot it, that depends on that. Okay, just like n1x, n2x, and so on. So we will see how it is plotted. Okay, something like n1 of x will be plotted, shape function 1, and so on. That is a cubic polynomials. And then we have lecture 4b. So we have using the principle of virtual work to obtain the stiffness matrix. So we will use principle of virtual work to obtain the stiffness matrix. Okay, how we, that is the elemental stiffness matrix, we can see how we will get the stiffness matrix. Okay, and then in lecture 4c, what we have, we will use Galerkin method to obtain a stiffness matrix. And in lecture 4d, we will use the solution of beam problem using finite element method. Okay, so what we performed in the lecture 2, now we will use the finite element method to solve that numerical examples. Okay, and the final, that is the lecture 5. Lecture 5 consists of what? Abacus modeling. So Abacus is a commercial software that is based on the finite element method, C0 FEM. So we will use Abacus then. Okay, so to model the modeling of one-dimensional beam, 2D, and 3D beam. Okay, so we will use that and we will compare our results with the Abacus modeling. So this is the syllabus what we are going to do inshallah in the next class. Thank you. Stop here.